Download this code from codegive.com, link in the description below. OK, let's dive deep into the column space of a matrix. This is a fundamental concept in linear algebra, and understanding it is crucial for grasping topics like linear independence, rank, null space, and solutions to systems of linear equations. I'll break down the theory, provide intuitive explanations, and illustrate everything with Python code using numpy. 1. The core idea: linear combinations of columns. What is a linear combination? Given a set of vectors, columns of a matrix, in our case, v1, v2, vn, and a set of scalars, numbers, c1, c2, cn, a linear combination is an expression of the form c1 v1 plus c2 v2 plus cn asterisk vn. You're essentially scaling each vector and then adding them together. The result is another vector. Column space defined. The column space, also called the range or image, of a matrix A is the set of all possible linear combinations of its column vectors. In other words, it's the span of the column vectors of A. If A is an mxn matrix, meaning it has m rows and n columns, then its column space, denoted as col, A, or im, A, is a subspace of R(m), m-dimensional space. 2. Geometric interpretation. The column space of a matrix is essentially the space that can be reached by combining the columns of the matrix. Here's how to think about it geometrically. Matrix with a single non-zero column. The column space is a line through the origin, aligned with that column. Matrix with two linearly independent columns. The column space is a plane through the origin, spanned by those two columns. Matrix with three linearly independent columns in R(3). The column space is all of R(3). When the columns are linearly dependent. If one or more columns can be written as a linear combination of the other columns, meaning they are linearly dependent, then those dependent columns don't expand the column space further. The column space is determined only by the linearly independent columns. 3. Why is the column space important? Solutions to linear systems. The column space is intimately related to the solvability of linear systems. Consider the system X equals B, where A is a matrix, X is a vector of unknowns, and B is a vector. The system has a solution if and only if the vector B is in the column space of A. In other words, X equals B has a solution if and only if B can be written as a linear combination of the columns of A. If B is not in the column space of A, then the system is inconsistent, no solution. Rank of a matrix. The rank of a matrix is the dimension of its column space. It tells you how many linearly independent columns the matrix has. A full rank matrix has a column space that has the dimension of the number of columns, or the number of rows if there are less rows than columns. Image/range of a linear transformation. When you view a matrix as representing a linear transformation, the column space of the matrix is the image, or range, of that linear transformation. It describes all the possible output vectors you can get from the transformation. 4. Finding the column space. Method 1, spanning set. 1. Start with the columns of the matrix A. 2. Identify the linearly independent columns. You can do this by row reducing the matrix A to its reduced row echelon form, RREF. The columns in the original matrix that correspond to the pivot columns, columns with leading ones, in the RREF form are linearly independent. 3. The linearly independent columns form a basis for the column space of A. 4. The column space is the span of these basis vectors. Method 2, solving X equals B. 1. The column space of A is the set of all vectors B for which the equation Ax equals B has at least one solution. 2. Set up the augmented matrix AB, matrix A augmented with the vector B. 3. Reduce the augmented matrix to its RREF form. 4. Determine the conditions on B for the system to be consistent, i.e., no rows of the form 0, 0, 0 C where C is non-zero. 5. Express B in terms of its free variables. This representation describes the column space. 5. Code examples, Python with numpy. Key improvements in the code and explanation. Asterisk reduced underscore row underscore echelon underscore form, A. Function asterisk implements Gaussian elimination to compute the reduced row echelon form, RREF, of a matrix. This is crucial for finding the pivot columns and thus the basis. Asterisk handles cases where the matrix has 0 elements. Asterisk uses a tolerance, 1e6, to compare floating point numbers, which is essential due to potential rounding errors. Asterisk column underscore space, A. Function asterisk takes a matrix A as input and returns a matrix whose columns form a basis for the column space. The logic is as described in the explanation above, RREF, identifying pivot columns, selecting the corresponding columns from the original matrix. Asterisk error handling asterisk includes a check for an empty matrix. Asterisk clearer comments asterisk the code is extensively commented to explain each step. Asterisk example usage asterisk provides clear examples of how to use the functions. Includes cases with linearly dependent columns. Asterisk illustrating if B is in COL, A added example illustrating Ax equals B. Row reducing AB will show you if B is in the column space of A. If, after row reduction, you get a row like 001, or 000 C with C non-zero, then the system is inconsistent, and B is not in the column space. Asterisk explanation of floating point comparison asterisk included because comparing floating point numbers directly can be tricky. Explanation of the code asterisk. 1. Reduced underscore row underscore echelon underscore form, A, asterisk. Asterisk the core of the algorithm is Gaussian elimination. It systematically transforms the matrix into RREF. Asterisk the code iterates through the columns, finding a pivot element, the element with the largest absolute value, in the current column, below the current row. Asterisk it swaps rows to bring the pivot element to the diagonal position. Asterisk it normalizes the pivot row, divides the entire row by the pivot value, to make the pivot element equal to 1. Asterisk it eliminates all other elements in the same column as the pivot element by subtracting multiples of the pivot row from other rows. Asterisk the tolerance variable is important because floating point calculations can introduce small errors. Instead of checking for exact equality to 0 or 1, it checks if a value is close enough, within the tolerance. 2. Column underscore space, A, asterisk. Asterisk this function first calls reduced underscore row underscore echelon underscore form, A, to get the RREF of the input matrix. Asterisk it then iterates through the rows and columns of the RREF to identify the pivot columns, columns with leading ones. Asterisk the columns in the original matrix A that correspond to the pivot columns in the RREF form a basis for the column space. This is because the column space is spanned by the linearly independent columns, and the pivot columns in the RREF indicate which columns in the original matrix were linearly independent. Asterisk the function returns a new matrix whose columns are the basis vectors. How to use the code asterisk. 1. Install numpy asterisk if you don't have it already, install numpy, pip install numpy. 2. Copy and paste asterisk copy the entire code, including the import statement, into a Python file, example column_space.py. 3. Run the code ** execute the Python file, python column_space.py. The code will print the original matrix and a matrix whose columns form a basis for the column space. Important considerations *** numerical stability ** Gaussian elimination, and RREF calculation, can be sensitive to rounding errors, especially with ill-conditioned matrices, matrices that are close to being singular. More sophisticated numerical techniques, like pivoting strategies, can improve stability. The numpy linalg module, example np.linalg.svd, provides more robust methods for finding bases for subspaces. Alternative methods the singular value decomposition, SVD, is another powerful tool for analyzing matrices and finding bases for the column space. It's generally more numerically stable than Gaussian elimination. Null space the null space, or kernel, of a matrix A is the set of all vectors x such that x equals 0. The null space and column space are related by the rank nullity theorem, rank A plus nullity A equals n, where n is the number of columns of A and nullity A is the dimension of the null space. Let me know if you'd like to explore any of these concepts in more detail, or if you have any other questions.